Our group looked at the problem of urban cyclist safety and created the automatic brake light cyclist safety system. My name is Hannah Dye.
My name is Jonathan Tan.
My name is Emily Xu.
And my name is Dominic Zajac, and we are JEHD.
The first article looks at different cyclist accidents, looking at the movement of the cars and cyclists to determine what types of crashes are most likely to happen. In this article, they found that the crashes in which the car collides from the side behind the bicycle and rear-ending the cyclist, and where the cyclist cannot see the vehicle, is the most common crash to occur. The second article looks at the effects of cyclist visibility on safety and how likely cyclists were to use visibility aids. It was concluded that cyclists weren't very likely to use visibility aids, but that the use of them greatly decreased the likelihood of crashes.
Our objectives are inexpensive, accurate, and easy to use. Because the whole project should cost no more than $50, it has to be inexpensive. We need it to be accurate to ensure the safety of urban cyclists. It has to be easy to use because it is inconvenient for cyclists to press buttons during cycling. There are three functions in our project. First, it should detect the high-risk collision situations to raise awareness of surrounding. Second, it should send warning to environment to prevent collision so that it can alert car drivers that the cyclist is slowing down. Third, it should increase visibility of cyclists to ensure that the car drivers can see cyclists even when it is dark. The two constraints of our projects are it should be less than 1 pound and less than 8 by 5 by 6 inch in total size to fit in the space under the bike seat.
Figure 3 shows that accidents happen frequently and don't just cause injury but can even lead to death. It is shown through a memorial put up to a woman who died due to unsafe cycling conditions in Berlin. Figure 4 shows how commuters are affected by urban cycling conditions. You can see just how close and personal cars can drive next to bicycles, illustrating how the infrastructure in the U.S. is not as safe for cyclists, since there are few bike lanes and cars can have difficulty sharing the road.
The problem we discovered is that cycling in urban communities is unsafe now, and accidents result to injury or even death happens a lot. So currently, no solutions are comprehensive enough to actively address this issue and enhance the safety of urban cyclists. So we believe that it's necessary to find ways that can actively respond to the cyclist environment and make sure that it is safe enough for cyclists to cycle in urban communities. So we want to design an inexpensive, accurate, and easy-to-use spark-fun system that detects high-risk collision situations, sends warning to environment to prevent collision, increases visibility of cyclists while weighing less than 1 pound with dimensions less than 8 by 5 by 6 inch, the approximate space under a bike seat.
While there are many products on the market dedicated towards bicyclist safety, many of these do not actively respond to the environment. For example, Bicygo's front and rear lights do not automatically turn on when the environment is dark and do not detect the acceleration of the bike to prevent rear collisions. These products are only passive and cannot react to the environment or the bicyclist's actions. Our product, using automatic components, address these issues.
From our literature review, we found that rear and side collisions are the most common type of collision for cyclists. So to combat this, we wanted to create a blind spot detector that would detect the presence of vehicles coming up from behind the cyclist from the left or right side and alert the cyclist correspondingly, as well as include a light in the front to increase the visibility of the cyclist at night.
We wanted a way to combat collision coming from behind, so we thought of a system that warns vehicles when a cyclist is slowing down, using red LEDs, which also increases overall visibility.
From our research, it was clear that poor cyclist infrastructure was the cause of many crashes in U.S. cities. We wanted to come up with a consumer product that could address this issue. For this solution, the cyclist location is obtained from a GPS and compared to Boston GIS data of high and low stress bicycle networks. This system uses this information to warn the cyclist if it is approaching an area where the road infrastructure causes cyclist commuting to become more dangerous. This is in hopes that the cyclists will be able to avoid these areas or at least be more cautious.
In our rank order matrix, we determined that it was most important for our device to be accurate, and then easy to use, and then inexpensive. We rated being accurate as 70, easy to use as 50, and inexpensive as 30. As you can see, we created a decision matrix putting a value for each design and objective. In the end, we decided on solution 2. It was inexpensive as the accelerometer was less expensive than a GPS module, and the ultrasonic sensor in the kit was not good enough, so we sought out more expensive ultrasonic sensors, which are more expensive than the accelerometer. Solution 2 was more accurate as the accelerometer was more accurate compared to the ultrasonic sensor, and it was easier to use because all it required was a switch and a button to calibrate.
Generally, the Arduino code reads in the accelerometer data, takes the average of the data, and compares that average acceleration to a threshold. If the value is below the threshold, then the cyclist is determined to be slowing down, which is a high-risk collision situation. Therefore, this portion satisfies our first functions. If the cyclist is determined to be slowing down, the red lights in the back light up, thus sending a warning to the environment. The code also increases visibility by comparing photoresistor values to a threshold and turning on the front LEDs if it's dark.
This is a photoresistor, which is one of our input components, LEDs, which are output components, an LCD display, which is also an output component.
This is the button used to calibrate, and these are LEDs used at output. And inside there's also an accelerometer used as one of our input.
So one of our most high-risk situations that we wanted to address was when it's dark out. So at nighttime, when there is very low visibility for bicyclists. So Dominic here is going to demonstrate how our safety system works during the nighttime.
Okay, so right now the system is off. To turn it on, there's a switch on the side here. You flip the switch, which turns the power on. And if you take a look at the LCD screen here, it sends a message to the user to press the button to calibrate the sensor. The button is located right next to the switch. Once you press it, the brake light blinks to indicate that it works. And right now, as you can see, the front LED is blinking, which increases visibility because it's currently dark outside.
So if it gets brighter, such as if the sun is out, then the LEDs are going to turn off.
So the daytime would normally be off. And the other function is the brake light, which activates when you're riding the bike and you brake.
Dominic is now going to demonstrate our safety system in action, looking specifically at the brake lights when he's slowing down. So we have Dominic here riding the bike, and then when he brakes, the brake light turns on.
So for our code, some code was referenced from a code found online, which came from this link here. This first slide contains mostly variables used to store some information for the code later on, as well as the naming the pins used for the different components, and also creating the liquid, the LCD display component. The setup begins by initializing the accelerometer and the LCD screen, setting all the pin modes for the input and output components, and then this is the calibration procedure used for the accelerometer. Next, this is the logic that's used to turn the brake light on based on the calculated average acceleration, which fulfills the detect high-risk collision situation, as well as the notify environment by turning on the LEDs. And this code controls the LCD based on the acceleration to display if the user is braking slowly, braking smoothly, braking too quickly, or if they aren't braking, just display their current acceleration. And the last function is to turn the front light on based on the light value, which is over here. The set target function is used for calibration. It also blinks the brake light to indicate that the calibration was successful. This is the function that sets up the accelerometer for reading data. This write to function was a helper function used in the previous one, and get acceleration gets the raw values from the accelerometer, and process acceleration converts those raw values into more usable g-force values. And get average acceleration gets the average acceleration of the accelerometer over a certain time period.
This is a bill of materials, and we get most of the things from SparkFunkit, and we buy the accelerometer, which costs $6.21, including tax and shipping from Amazon. We also get an Ethernet cable, which costs $8.15 from Economy Hardware. So the total expenditure is $14.36.
So this is the fritzing diagram for our project, which, as you can see, contains the GY521 accelerometer, our brake-in-front LEDs, as well as the photoresistor and LCD, which make up all the components of our project. This is going to be important to have for next semester so that in case we need to take the project apart or rebuild it or modify it anyway, we know how the circuit is assembled so that we can recreate it next semester.
At this point, our project performs all of the functions. It detects high-risk collision situations using the accelerometer. It prevents cyclists from getting rear-ended through sending a warning to the environment in the form of red LEDs when the cyclist slows down. Visibility is also increased since the bike light in the front works by turning on when it's dark. It satisfies the constraints weighing only 0.5375 pounds, and when the front and back boxes are placed together, the dimensions meet the requirements. The objectives were also met as it costs only $14.36. It accurately detects when a cyclist brakes and is easy to use as the user only has to flip a switch and push a button.
As you can see, there are two boxes. The box on the left goes underneath the bicycle seat and the box on the right goes next to the handlebars. The accelerometer reads in acceleration data, and if the bike is slowing down, the LEDs in the back, the red ones, turn on as brake lights. The accelerometer also sends data to the LCD, whose brightness is controlled by the potentiometer. The photoresistor reads the light data from the environment, and when it's dark enough, the LEDs turn on in the front. The most challenging part was getting the accelerometer to work as intended. What surprised us most was when you tilt the accelerometer, it gives an acceleration reading even though it's not moving, so we had to perform a calibration technique to combat this. The easiest part of the project was the photoresistor, as it was similar to the spark-front circuit.